Hi, everyone. So we will continue with the session here. So, yeah, do you, please? So we are here to talk about the ecosystem enabling of liquid cooling ingredients, which is work that we're doing at Intel. So there's a team working at Intel on the ecosystem enabling. And me then, I'm Jessica Gullbrand, engineer at Intel, but I'm also leading the cold plate work stream. So I'm going to talk a little bit in the end of this presentation about that as well. And my colleague, Mark Sprenger here, will be doing part of the presentation as well. So we do know that there's a continued demand, and we've heard that throughout the presentations here today as well. There's a continued demand for increased compute performance, and we see that power and power densities are increasing. So we need more efficient cooling than air cooling. And one of those cooling technologies is liquid cooling. Liquid cooling is not new. It's something that's been around for quite some time. So it was introduced in the mid-60s while cooling mainframes and lasted for a few decades until CMOS technology was developed and introduced and accepted in the industry, and the power levels and power densities came down. And then air cooling really became the most efficient cooling technology for the lower power and lower power density components. And yes, we can also achieve higher densities, right, when we liquid cool systems. So Intel is working then with suppliers to enable liquid cooling ingredients. And it's really, why are we doing that, right? And it's really, we want to be able to increase the availability of liquid cooled ingredients. We want to be able to make sure that the risk is as low as possible when implementing liquid cooled solutions. We want to make sure as well that there's generational and system supplier compatibilities as we're going from one generation to another. And we talk about interchangeability, and that's part of what Mark will be talking about just in a few minutes. And we can also allow for faster time to market opportunities for OEMs. So that's really all the reasons behind it, why we're doing this. And the focus is on manifold distributed liquid cooling ingredients. So we're focusing on the secondary loop ingredients. So secondary loop, just to make sure that we're all on the same page. It's really from the CDU going to the rack, through the manifold, through the IT equipment, and then back again. And specifically, the four ingredients that we're focusing on here is the cooling fluid, the CDU, liquid to liquid CDU, and as shown here, where our initial step is to look at an in-rack CDU. And we also gonna then talk about interchangeability and universal QDs, and that's part of what Mark will be talking about, as well as, of course, cold plate designs for the high power components. So the rest of the presentation, the outline of it is talking about these four secondary loop ingredients, the cooling fluid, the UQDs, the CDUs, cold plates, and then summarize it in the end. And really, everything starts with the cooling fluid, the selection thereof. So the wetted materials and cooling fluid compatibility is, of course, extremely important. You want to make sure that you do have material compatibility with all the different ingredients that you're going to use. And also here to define the wetted materials. So wetted materials are all the materials that come into contact with the cooling fluid. You also need to determine, of course, what the quality requirements are for the fluid in order to reduce any type of risk of corrosion, fouling with having insoluble particles, scaling with the salt deposits, and microbial potential bacterial growth in the fluid itself. You need to work with the fluid manufacturer in order to understand what the maintenance requirements for the fluid is. And really the cooling fluid options that we have here is having water with additives, glycol-based or dielectric fluids. And the one that Intel has chosen to work with is the propylene glycol. And we're choosing PG55 and PG25. So 55 is the 55% glycol. We use that for storage and shipping. And the PG25 we use for operational conditions. We have determined a wetted materials list. So this is the wetted materials that we have material compatibility with for the fluid. So I should say also the fluid selection was done from a multi-source perspective and to make sure that it's fluids that are available globally. That's where the selection came from. Here, we have the wetted materials list. It's fairly small at this time, right? So but these are the materials that we today feel comfortable with, that we have material compatibility with the different PGs, propylene glycol cooling fluids that we're investigating and have chosen. And we have elastomers, plastics, and metals on this list. What we haven't added on yet are bracing materials because we're currently testing those. So that will be added on later. And I should also mention that this doesn't mean in any way that this is the final list and the only wetted materials that potentially can be used. It just means that these are the ones that we have tested. You could potentially add additional ones, but of course you need to do a diligent testing of those. And the fluid operating range, so this is in order to meet Intel requirements for shipping and storage, need to make sure that nothing freezes if you're shipping it charged down to minus 40 Celsius. That's why the selection of the PG55 was done. While the higher temperature here goes up to 70 Celsius. It comes from the Intel requirements. The operational temperature, we have selected from the ASHRAE recommendation, the 17 Celsius, which is based upon the dew point. And the 65 degrees comes from an analysis that we have been doing in order to determine what type of temperatures that we see in the cooling fluid leaving the IT equipment going to the CDU for different type of server and rack configurations. So that's where that's coming from, and I will hand over to Mark.
Thank you. Right before I stepped up here, I was talking to Jim, my manager back there, and he said, if you were to graph a person's ability to be attentive, it spikes down at like 3 o'clock. I said, we're presenting at 3, so I hope you've all had your coffee. What I'm going to talk about is universal quick disconnects. We have this as part of, as Jessica said, we have this as part of our initiatives to make things common and compatible in the market and to proliferate this into an ecosystem that's capable of responding to the need when the need arises. What we did is we're working with 5 different suppliers and we're creating a universal spec. The universal spec will be contributed to OCP, and this spec will be what suppliers go by to develop this universal quick disconnect. The interface and the performance, what we've done is we created a minimum spec. The minimum spec is so that the suppliers will have a maximum opportunity to proliferate their own IP and their own style of connector, even though they're going to be universal and they'll fit together. So, like I said, we're working with suppliers. We're doing this in 2 phases. Phase 1 is the handmade connector. Phase 2 will be a blind mate connector. These connectors right now, we've been validating those internally. Intel is validating the interchangeability aspect of the quick disconnects. The interchangeability of all the samples that we received work perfectly. Put them all together, they connect, they flow. We ran CV value testing on all these connectors, and they all meet the minimum requirement. Most of them exceed the minimum requirement, as a matter of fact. All the interchange parts also meet the minimum requirement. So that's really the piece that we need. Intel will also validate the ability for these connectors to hold together at high pressure. So we're specifying a 100 PSI connector, and we're using a 3x safety factor. And so we'll be testing those with all the various connection types that the suppliers are providing at 300 PSI. I have a couple examples up here. I have I've got a Staubli plug, and I have a CPC socket and a Staubli plug. And as you can see, they connect, they fit together. And likewise, I have a CPC plug and a Staubli socket. And I got the Staubli guys in the audience are making me nervous. And of course, those connect together as well. So, so it worked perfectly. We've ordered a number of parts so that we can finish our validation. And we will have the first UPD04 universal part available at the end of Q2. You can go to the next connection, next slide. So how do we make this happen? What's the minimum spec look like? This is what the profile of the minimum specification looks like for our UQDs. You'll see that the plug side, which is what you see on the right there, has a fairly unique shape to it. And this is what allows you to have a sleeve ball lock type connector mate with a connector that also mates with this thumb lock type connector. So this is the shape that allows that to happen. It's very unique for connectors. You're probably all familiar with pneumatic connectors. They all look very much alike, but in this case, suppliers are allowed to differentiate themselves with this type of connection, where we can have really an infinite number of locking mechanisms, right? So we've minimized the spec to maximize the opportunity for suppliers to differentiate and innovate in the space. Next slide. And this is what the spec looks like, and this is what will be ultimately delivered as part of our Intel's contribution. This specification, you can see that the plug side has quite a, let's say, more rigid in terms of its spec, more rigid in terms of its dimensional spec, and the socket side doesn't have as many dimensions that define it. Only the areas that are required for interchangeability. And so this is how we get interchangeability into the system. Interchangeability, you notice we have two phases, phase one, hand mate, phase two, blind mate. Why is that? Because we're focused on between the cabinet and your IT equipment. That's where we really want interchangeability, because oftentimes your IT equipment is made by one supplier, delivered to an integrator who pulls the parts together. At the cabinet side, you have universal connection, you have a much simpler ecosystem. And so that's what we're doing with UQD. I believe that's it for UQD.
I believe so. And there's also, just because Mark was only bringing up a couple of examples and prototypes here, we have more as well. And we'd be outside of this meeting room here if you want to have a look at them as well. And it's really, as Mark was saying, it's really the interchangeability that we're after, right? You want to be able to have an OCP rack with quick disconnects, right? And you'll be able to upgrade when you need to, pull one server out, put in from a different server. As long as you have UQDs, it doesn't necessarily matter who actually created the server for you. So the next topic here then, or we continue down the line, right? So we had 4 different ingredients in the secondary loop. So the third one is the cooling distribution unit. And we started, right? look at in-rack CDUs. The other options that you have is, of course, end-of-row CDU, where you have a CDU providing cooling for several different racks, or in some cases as well, a virtual CDU if your facility water really meets the quality of what you need for your IT equipment cooling. You have liquid-to-liquid CDUs and liquid-to-air CDUs as well. And as what we have done at Intel then is our initial investigation includes in-rack CDU and liquid-to-liquid. It doesn't mean that the work that we're doing cannot be applied, of course, to end-of-row CDU as well. So what we've done here for CDUs is really look at what the parameters of importance are. What are the parameters that you need to consider, right? So this is, of course, in comparison to your specific installation, to the specific cooling fluid that you're using as well. So what is of importance here is really the L10 pump life, so time taken for 10% of the population to reach failure for your particular fluid and your particular installation. This data can, of course, be hard to get your hands on as well. System mean time between failures as well. Mechanical, are there any aging effects that are happening? Are there any leaks that are going to occur? Any gaskets that needs to be replaced, for example. Chemical, again, the material compatibility to all the wedded materials. So you need to work in close collaboration with the CDU suppliers in order to understand exactly what type of material that have been used in the CDU. Again, it's essential to have material compatibility between the cooling fluid and all the wedded materials in the loop. You need to understand the heat exchanger thermal performance, right? And if there's any changes of that over time. And for the specific fluid that's selecting. You need to understand the pump performance and if that changes over time as well as potential here for thermal cycling, both from an operational point of view and non-operational, more from storage, shipping, and then to bring up. But each of this, so it's really of high importance to do an FMEA, right, of failure mode effects analysis in order to determine for the particular CDU and fluid that you're using, where are the highest risks? What is it that you should focus on when you do a detailed validation and qualification plan for that? So we've worked with several CDU suppliers in collaboration on this as well. And then the last ingredient talking about the cold plates. And the cold plate design needs to, of course, meet your cooling requirements for the specific fluid that you're using, the temperature that you can provide to it, and the flow rate that you can provide. And there are many different shapes and options for cold plate designs, really. I'm just showing a couple of examples of microchannel cold plates here, where you have flow, for example, going in one side of the cold plate, go through the microchannels, come out in the other end, or you could potentially have the fluid enter in the center, then split up, go into microchannels on each side, gather again, and go out. So depends upon what you need, right? Of what which cold plate design that will be able to get you there. So next one, thank you. And also for cold plates, what parameters to consider there in the same way as we're looking at for CDUs. It's material compatibility, of course. Again, we continue to stress this throughout the presentation, so hopefully the importance of that is coming across. And specifically, of course, all the different parts of the cold plate and what I mentioned in the beginning as well, right? In the wedded materials list, we did not, or we have not yet added the bracing materials because we are currently testing those. Which ones have material compatibility with the fluid that we have selected. They also have need to meet the internal pressure ratings, right, of the IEC standards of either 2 times or 3 times the pressure. You need to meet the mechanical requirements. So if you're putting in your cold plate and load it, right, you need to be able to take that load and have enough stiffness and meet those requirements. You need to fit the cooling loop inside of the IT equipment. You need to understand where your operating conditions are, the operating pressure, flow rate, what temperatures can you really allow, both from inlet and outlet temperatures. And for the microchannel design, cold plate design, the parameters to vary there is really fin area coverage, the height of the fins, the pitch, the length, the thickness of them, in order to generate the design that you need. Okay? So in summary, Intel is working on the ecosystem enabling of liquid cooling ingredients in the secondary loop. We have selected a cooling fluid, PG 55, so propylene glycol 55% or 25% for operation, right? 55 was for shipping and storage. We have developed, as Mark was showing here, the universal quick disconnects, which we are contributing to the OCP. We have discussed as well the cooling distribution unit. We're working with several CDU suppliers on this in order to determine what really of validating the designs, right? So what we want to make sure here as well, we're looking at different ingredients. So that we, in the end, can come up with recommendations for a full cooling solution versus looking at ingredients in separation. And yep, so as I said, Intel is contributing the interchangeability of the UQD and other information to the OCP through the cold plate work stream. Next one. So this is the rally cry of please get involved, please attend the cold plate meetings. Next meeting will be on Wednesday, 11 a.m. Pacific time. So hope that we're getting more people involved in these discussions and be able to contribute more. So what we have right now for the cold plate work stream, we have a start of wetted materials list. We have the UQDs. We started of having concepts and a few designs for manifolds for the OCP racks. And those are the type of discussions that we're currently having. So with that, I hope to talk in more details during the cold plate workstream meetings. And now we do have time for questions. Yes, Rolf?
You mentioned for the temperature tolerances, you're taking 65 degrees Celsius as the maximum. It feels like it's a bit on the low side. Is that correct?
So the question was that for the operating range for temperature, we have selected 65 degrees Celsius. Isn't that on the low side, was the comment. We have done that through analysis of looking at from a, how should I say that, making sense of different server solutions and different power densities into a server. And comparing that to where we are today in regards to air cooling. What we're seeing that if you're getting into, there are some limitations of how much power you can really get into a rack as well, right? And then depending upon how many CDUs, if you're looking at either the in-rack CDUs versus end-of-row CDUs as well. And with that, it's basically a big mix of different parameters, of looking at different scenarios of where for some solutions where it makes sense to stay with air cooling versus going to liquid cooling, from that analysis, we have come up with in the configurations that we see today, 65 degrees is an upper limit. So hopefully that, huh?
Do you expect it to increase over time in the future?
It might, right? It might. The higher density and the higher power parts that we get, but right now we're dealing with what we have today.
That's the maximum operating temperature as opposed to the maximum, say, stagnation temperature, correct?
Yes, it's the maximum fluid temperature, right, of the cooling fluid at operating. Yes, not if you're saying that you would have a failure and it fluid would stop running. Of course, it would heat up more than that.
And the components would be expected to be able to withstand that, correct?
Yes. Yes.
I think I heard you say at the beginning that you're using 55 and 25 propylene glycol, but you were leaving it somewhat general so that you can use any propylene glycol. My question, my comment, I guess, is so different suppliers propylene glycols all have different inhibitor packages, all have different biocides. So to me, in order to put a wetted materials list out there, you have to call out the specific propylene glycol that you've used to do your analysis.
Exactly. I'm totally with you. And if that came across, that, yeah. Yes, thank you.
Thinking that they can just pick and choose different pieces of everything and put them together because it doesn't work that way.
No, it doesn't. It doesn't. So I totally agree. And what I couldn't give you today is the supplier names of, and the specific liquid. So we've been working with 2 different fluid suppliers with specific liquids. Of course, we can't take liquids from different suppliers and mix them, right? And this wetted materials list is accurate when it comes to those particular fluids, right? And that's part of what we're going to contribute to the OCP as well. We're just not in the position of being able to release the names at this point. So thank you for clarifying that. Jim? This is, for you that don't know Jim, he's my boss. So thanks, Jim. So we hope to be able to do that actually very shortly. So within a month or 2, we're hoping to be able to provide those names. Dale?
So, Mark, you have 5 suppliers of the Quick Connects. I'm a buyer. I buy the lowest cost one. What's my downside risk?
Well, as a buyer, I would encourage you to do your due diligence in terms of which suppliers you're selecting for any parts in your system. I think that would apply to quick disconnects.
So what would be the factors that I would look at that I would disqualify, say, the bottom 3 and select the top 2?
So while we have a minimum spec, if you are designing your system to a minimum spec and that minimum spec satisfies your requirements, then all the suppliers will be making parts that meet the minimum spec. We fully expect the suppliers to in lots of cases exceed that specification. So your specific requirements would have to be aligned with that particular supplier. And
so
if you had
400 PSI rather than 300, then I would...
then you pick up the phone and call the suppliers. Yep.
Did you use a dielectric fluid?
We have not. No, we selected a propylene glycol fluid, and that's the one that we have been testing with. But I should say also from the cold plate workstream perspective, right? I'm not saying that there will only be one solution, right? As I was mentioning here, there's different fluids that can be used, water-based, right? Glycol-based, or you have dielectric. And what we can contribute is what we have done, right, of being able to provide, of saying that here's the supplier names, here's the wetted materials that we work with that, and here's the suppliers for CDUs and cold plates that we've been working with, right, because we have done the testing. And anyone else that has done similar testing for dielectric fluids or for water with additives and can provide similar information, that's more than welcome, right? So it's not, we want to make sure and enable liquid-cooled solution. We're not, we're not married to have one. But there's only so much that we can do. So that's why we're looking for more engagement and for more contributions within the cold plate work stream.
There's a question back here.
Yeah, in terms of the temperature, the operating range of the selected 7 to 70 degrees inframarginal dew points, right?
The 17 is Celsius, yeah.
You selected that because you didn't want condensation in your lines.
Yes.
Okay, so there's a lower limit in terms of the operating temperature that you can send into your unit, depending on the
Put,
So it depends on your location. You're kind of restricted in terms of the humidity and your environmental temperatures when you're selecting the right? So there is some interface, I think, with the solutions that you're suggesting and the data center facility group in terms of
yes.
HVAC design.
Yes, yes, it is. So these are the guidelines and recommendations that we're giving. It doesn't mean that it won't work until, depending upon your environmental conditions around it, that it won't work in a different, right? All that you're really after is not to have condensation. Yes.
As you know, within immersion, server optimization is a big thing. Do you expect any specific, unique optimization advantages in combination with cold plate on server design?
On server design. That's an interesting question. I'm sure that there are ways that we can optimize and change and make things more efficient in the server design if we're using cold plate or liquid cooling or immersion, right, solutions. But I don't, I can't say what those are today.
But it's not part of the work stream, I mean.
No, it's not part of what we're currently doing, right? We're currently enabling the ecosystem with these secondary loop ingredients. Okay, sorry. Maybe we can take this afterwards because I'm checking time here and I'm running over and we all know that Rolf wants to talk.
Actually, I'm the last person.
Okay, Nigel.
The question that I was going to ask is about the attachment of the cold plate to the actual socket and the screwing mechanism. Is that screwing mechanism and the specific holes available for the respective suppliers to be able to access to attach the cold plates?
That's a little bit,
Are you asking
trickier.
through OCP or through Intel?
yeah, that's what.
Putting out cold plate designs, but how do we actually attach them to the
Yeah,
so
and
Intel would continue to provide guidance on the socket loading and that type of information.
as anyone else would do, right? That is selling those similar type of compute, right? So that's nothing that I see that can be provided as an open source.
What's the leakage with the on
On the
these connectors? So we specify a acceptable leak rate that would essentially create a non-drip connector, and there's several folks in the room that'll give you a better answer for this, but essentially there is some amount of fluid that would still exist on the system, but as long as it's not dripping is the goal of the spec. So each of the suppliers would provide a spillage rate that you could get. There is a spillage rate that is in this specification, but I think the suppliers exceed that. So.
Yep. So it will be supported or given in the requirements as well.
So on that, is there a containment strategy for any potential leakage? So let's say a connector would
You're talking specifically for the connector?
Well, many of these do have a sort of backup O-ring that exists in there, so you have that. But if you were to fail both O-rings, it's going to leak. Yeah.
So is there something in the rec features or how
It's
That's interesting because that was part of the last cold plate workstream meeting that we had, talking about leakage mitigation and trying to gather from the participants, right, of how important is really leakage mitigation, right? And it's not anything that we have currently addressed, but it's something that we need to address, right? As long as the interest and the concern, right, is there. Exactly. I mean, you're doing a design to minimize the potential for any type of leakage, right? So the trick here is really to understand what the concern is, right, for leakage. Is it something that you potentially would put in more hardware in order to prevent, or in that case, how much is it worth to you to do that, right? And to what rate? Where do you want to put it?
Yeah,
Yes,
we look at a
yeah.
multiple-pronged approach where you design the system so that it won't leak, number one. Then you design a system that maybe it detects the leak, and then what do you do after you detect a leak? What happens then? So there's a number of things we have been thinking about in terms of leak mitigation.
I'm thinking about different mitigation strategies, but again, it comes at the cost as well, right? So what cost are you willing to pay for it? Is it okay for you to go in and have it, be notified by manually shutting it down? Or do you want the, electronic safe shutdown of your system if you're detecting a leak? Or do you want to have a shutdown electrically as well as the fluid, right? So that just increases kind of the complexity and therefore also the cost of it. So we're going to continue in next cold plate meeting on Wednesday to continue those discussions of how important is leakage mitigation and intervention, really, detection and intervention of leakage for different participants, and hopefully go from there. So we're definitely having discussions about it. Okay.
One last one?
One last one?
just in terms of your experience with the plastic materials, particularly HDPE, like the plastic, the non-metallic fittings, at the temperatures, something about knocking off them, like 50, 60, 65. Are you having problems finding fittings that meet that 100 PSI rating that you mentioned?
For plastic couplers, at the high temperatures. So that's probably a better question for the suppliers, but I don't think there's a problem meeting it, no. No. No.
Okay, great. Thank you. And Rolf,
Thanks for the questions.
take over. Yeah, thank you for the discussion. Appreciate it.